Okay. Hello, everyone. Welcome to our final presentation. My name's Patrick.
My name is Eddie.
Okay. Here's our project overview. In this project, we're using UCI's heart disease dataset to implement machine learning to predict whether a patient has heart disease based on medical factors. In this project, we trained and compared three classification models. We implemented logistic regression, decision trees, and random forests. These models were then evaluated using accuracy, recall, F1 score, as well as confusion matrices to help us determine which three classifications were the most reliable predictions. The ultimate end goal for us was to demonstrate how machine learning can support early detection of heart disease and assist in making more informed decisions. Here's a quick overview of our variables table. I won't go too deep into this because we cover what some of these variables mean later on, but I did want to point out that on the right we have our binary target. 0 means that there is no heart disease present, while 1 means that there is heart disease present. And here's a feature correlation heat map. The target column is our most important column as it indicates if a feature correlates with having heart disease. Warmer colors indicate positive correlation and colder colors indicate negative correlation, and lighter colors indicate that there are no correlation. As we can see from the graph, abnormal thalassemia and more blocked vessels, exercise-induced angina, and higher old peak values all correlate with more likely to have heart disease, while thalach, meaning higher max heart rate, has a negative correlation with heart rate. Um, This means that the higher someone's max heart rate is, the less likely chance they will have a heart disease. There are also relationships with some features like old peak and slope having a positive 0.58 correlation, while age and thalach having a negative 0.38 correlation. Next is our distributions for all our features. As you can see, age and thalach have roughly bell-shaped distributions, while T-rest BPS, the resting the resting blood pressure, has approximately normally distributed distribution, and then old peak and cholesterol have right skewed distributions. And the graphs with two columns are our binary features, and the ones with more than two columns indicate categorical features. And then let's move on to our notebook as it'll be better for showing you our code. So we begin by importing our libraries. We use pandas, NumPy, Matplotlib, and Seaborn. And here in this section, we're loading in our data with pandas. Um, df.head prints out our first five rows. And then next is our basic data set info. As you can see, we have 303 observations and 14 different targets or 14 different features. Next, we have our summary statistics, and this shows us our basic statistics for each feature. So as you can see right here, we have the count, the mean, standard deviation, and then our interquartile ranges. Okay, and then first we are converting our missing values. So any values marked with a question mark in the data set are replaced with not a number, so null values in this case. And as we can see, there are four missing values for CA and two missing values for thal. And then here we're just converting our columns to numeric, and this helps us with our analysis later. And here we are just are checking our missing values again, and we still have four missing values for CA and two missing values for thal. And then here we're duplicating or checking for duplication or just duplicate rows. And um, as you can see, we have 0. But if we did have duplicated rows, we would just take those out because it would lead to overfit. And then here we are converting our targets to binaries. So this was the target binaries that I was mentioning earlier. 0 indicating no heart disease present and 1 indicating that there is heart disease present. And then here we are checking for class balance. we can see that there are 164 patients with no heart disease present, while there are 139 patients with heart disease present. And then here's a graph to visualize our class balance. We can see that it is about equal with about 20 off. The patients with no heart disease have 20 more. Here is the code that we use to implement our heat map that I showed earlier. And then here is the code that we use to implement our feature distributions that I also showed earlier. Okay. And then here we're splitting our features from the target as the targets would be the outcome, and we want to separate that for our training set and testing set. Once we split them, we have our feature shapes, which are 303 observations or rows of observations with 13 features, and then the target shape would just be the 303 rows and one column. And then here's our training and test split. We're splitting our data set into 80% training and 20% test. So as you can see, here's the shape of our training set. We have 242 rows with our 13 features, and then the testing set is 61 rows with 13 columns. Okay, and then, so first we need to impute any of the missing values after we split. And when we were working on the project, we had a problem where we where we split and then imputed, but we actually need to split before imputing because this helps us avoid data leakage. And if the missing values were to be filled before we split, then the median would just be calculated from the information from the entire data set and not just the test set itself. And we chose to impute with median because the two features that had missing values, CA and thou, they aren't guaranteed to follow a symmetric distribution, and a median imputation is more resistant to extreme values, while mean is more influenced by its outliers. The median overall provides a more representative value while preserving the integrity of the dataset for model training. And so here we're creating the imputer and then we're fitting only on the training data, and then we're applying the same medians to the test data. Okay, and then now let's prepare the data for modeling. Here we are scaling our features. Many machine learning algorithms perform better when numerical features are on a similar scale. So this is most important for logistic regression because logistic regression is sensitive to differences in feature magnitudes, and scaling helps the model learn more effectively by standardizing the feature values. Decision trees and random forests do not require scaling, but using scaled data for logistic regression ensures a fair comparison across the three models. And then here's the implementation of our first model, the logistic regression model. And the purpose of this is to train the first classification. And logistic regression serves as a strong baseline because it is simple, interpretable, and commonly used for binary classification problems, such as this one where we're dealing with whether patients have or don't have heart disease. Okay, and then next we're gonna make predictions with our logistic regression. And this step uses the trained logistic regression model to make predictions on the test data. The test data represents new unseen patient records, so this helps us evaluate how well the model performs outside of the training set. So here we have printed out our first 10 predictions. Okay. And then next we are going to evaluate the logistic regression model with the printout of the first 10 predictions. Now that our model has made the predictions, the next step is to evaluate them, which is what we're doing right here. And instead of just relying on accuracy alone, this section also calculates several other evaluation metrics that provide a much more complete picture of the model's performance. And these metrics will also make it easier to compare our logistic regression with the decision tree and random forest models later in the project. So here we can see the calculation that we're doing. Here's the calculation for accuracy, the calculation for precision, recall, and F1 score. And right here is a printout of our performance. Okay. And then the last part we have for our logistic regression is our confusion matrix. And the confusion matrix provides a detailed breakdown of the model's prediction by showing how many predictions were correct and where the model made mistakes. So this visualization is especially useful for medical classification problems because it highlights false negatives. So all the patients with heart disease who were predicted as healthy and false positives. So all the healthy patients predicted to have heart disease. Yeah. So here's our true positive, and then here's our false or true negative. Yeah. Okay.
Okay. And then the process is pretty much the same for our other models. For our second model, it is the decision tree. And for this specific chunk of code, the purpose of it was to train the decision tree classifier and compare performance with logistic regression. Decision trees learn by creating a series of decision rules based on the input features, making them easy to interpret and visualize. Unlike logistic regression, decision trees do not require feature scaling. And so what this chunk of code is doing is that it imports the decision tree classifier from scikit-learn, creates a decision tree model with a fixed random state, so the results are reproducible. It trains the model using the original training data, and it does not use the scale data because decision trees split data based on feature values and are unaffected by differences in scale. And the next chunk is a continuation of our decision tree. For this specific chunk of code, it uses the trained decision tree model to predict whether each patient in the test set has heart disease. It calculates the same four evaluation metrics used for logistic regression, which are accuracy, precision, recall, and F1 score. And it also stores the metric values so they can be compared with other models later. For the next chunk of code, it generates a confusion matrix using the decision tree predictions. It displays the results as a heat map. And as you can see, it shows a number of true positives, true negatives, our false positives, and our false negatives. For our next model, it was random forest. And what this specific chunk of code is doing specifically is that it imports the random forest classifier, creates a random forest model with 100 decision trees, and it uses a fixed random state so the results can be reproduced. Pretty much the same process as our other models. And this trains the model using the original training data. However, unlike logistic regression, random forest does not require feature scaling, so we continue using the XTrain and XTest. And the reason why we're using random forest is because it is often one of the strongest baseline models because it combines predictions from many decision trees instead of just relying on just one, as well as it is less likely to overfit than a single decision tree. For our next chunk code, it is chunk 27. So this step uses the trained random forest model to make predictions on the test set and evaluates performance using the same metrics as the previous models. So this keeps the model more consistent. And then for our next chunk of code, chunk 28 creates the random forest confusion matrix. This obviously helps visualize the performance of the random forest model using the confusion matrix. It allows us to see where the model made correct predictions and where it made mistakes, making it easier to compare against the logistic regression and decision tree models. And what this chunk of the code is doing is it creates the confusion matrix using the random forest predictions, and it displays the matrix as a heat map as well as our previous models. It shows the true positives, the true negatives, the false positives, and the false negatives. Okay. Topic 13, this is our model comparison. And the purpose of this step is to compare the performance of the logistic regression, decision tree, and random forest models using the same evaluation metrics. This comparison makes it easier to determine which model performed best for predicting heart disease. And what this chunk code is doing is that it collects the evaluation metrics from all three models, creates a table that displays each model's accuracy, precision, recall, and F1 score, and it rounds the values to 4 decimal places for a much more cleaner presentation. And the reason why this is so important is because instead of looking at three separate outputs, this table lets you compare the models side by side. And it helps us answer the questions such as which model achieved the highest accuracy and which model had the best recall. And so for our next topic, feature importance, the purpose of this step was to identify which patient characteristics had the greatest influence on the random forest model's predictions. This serves as an additional KDD analysis beyond simply just training models and helps explain the factors most associated with heart disease prediction. And what this chunk code is doing specifically is that it retrieves the importance score assigned to each feature by the random forest model. It matches each score with its corresponding feature name, and it sorts the features from highest to lowest importance, as well as it displays a table showing which medical variables contributed the most to predicting heart disease. And the reason why this is important is because it goes beyond asking which model performed the best, and it answers the question, what information did the model find most useful? So for example, you can find features such as chest pain type, the number of major vessels, which is CA, the maximum heart rate. And these findings help explain the model's decisions and provide meaningful insights that you can discuss um, with our findings. Oops. Okay. And then for our feature importance, yes, this step creates a bar chart for the, wait, is this?
This one.
It's the next one, yeah. So this step creates a bar chart of the feature importance scores calculated by the random forest model. The visualization makes it easier to identify which medical features contributed the most to predicting heart disease and provides an additional analysis beyond just model evaluation. And yeah, we can see from here that our character or our feature that has the most amount of importance is our phthalate, which is our maximum heart rate. And then for our next topic, discussion and model selection. Excuse me. Is this, yeah. The purpose of this step is to automatically determine which machine learning model achieved the highest accuracy. This provides a more clear conclusion to the model comparison and supports the final recommendation for predicting heart disease. And what this chunk code is doing specifically, it looks through the comparison table created in the previous section. It finds the model with the highest accuracy, and it prints all of its evaluation metrics, as well as it provides a clear summary of the best performing model. So rather than manually comparing three different models, this section clearly identifies the model we would recommend based on our evaluation metrics. So after evaluating all three machine learning models, Random Forest achieved the best overall performance and was selected as the final model for predicting heart disease. And for our next, pretty much is reinstated what I just said, but we have a conclusion. In this project, machine learning techniques were used to predict whether a patient has heart disease based on their medical information. After performing exploratory data analysis, handling missing values, and preparing the data, three classification models were trained and evaluated. 1, logistic regression, 2, decision tree, and 3, random forest. The models were compared using accuracy, precision, recall, and F1 score to determine which one performed the best. Feature importance analysis also provided insight into which medical variables have the greatest impact on the predictions. Overall, this project demonstrated how machine learning can be used to support heart disease prediction and assist in making more informed healthcare decisions.
And then that is all. Thank you.
Thank you.